Welcome to the Brainstorm with Sparks and Finn, a podcast where we brainstorm the science and philosophy of a new age, an electric universe age, and what it means for the human race, past, present, and future. I'm Finn, author, host, and still clinging to sanity, still breathing. As for Sparks, well, let's just say he's going through a rough patch.
I'm a positron!
You look like a positron.
It's ridiculous.
I show up whenever I'm needed!
Today's guest, no big deal, just the super genius who invented the structured atom model. What? Introducing Edo Kaal, lover of nature and geometry, whose revolutionary work will change the way you reality. Eureka! Today's springboard topic, the structured atom. So battle stations, people. It's time to fire Mr. Kaal into the dark heart of mainstream particle physics. May God have mercy on their souls. Hello.
Hi, there you are. Wow. I was telling Edo it's been a long time since we've all chatted.
It's been ages.
Oh my goodness.
All right.
Yeah, how long did you guys talk after I left?
Oh, geez, probably two hours. I think we got off the phone about midnight, wasn't it?
Oh my goodness, because Edo and I were talking for almost 2 hours, and you guys talked for 2 hours. So
Poor guy.
I'm surprised
seems
Edo
like
has any talk left in him.
Well, we'll find out. It's very early in the morning, but I'm afraid that these topics that we're talking about can be endless talk.
Very true.
Which is not a bad thing.
No. So, well, there's a lot of things we can point out or take in isolation or take a broader perspective. There's so much we can talk about. So, yeah. What are we going to talk about? The electric universe, nuclear physics?
Yes.
Well, I would like to know how you got interested in electric universe first off, and then find out what your kind of area of expertise in what you'd like to talk about today is.
Okay. That brings me back. Long ago, I started out my life with studying environmental chemistry. Couldn't find work in the sector, so went to the IT sector like so many others in that era. Worked about a decade in the sector. Then I had my, how does one say that? My falling out of life, everything goes against you. You lose stuff, material stuff mostly, but also, personal relationships and whatnot. It brings you down, back to yourself. You start thinking, life sucks, it hurts, it's painful, etc., etc., etc. But in the end, you find out, maybe I needed that. What it did is it brought me back to myself, and I started to do some thinking, and I went back to my old science, to my old love, science, if you will, right?
Yeah.
That's what my original studying. So I picked it up again, see if I could, reform myself again into something of a scientist that I found much more attractive than the IT sector. And lo and behold, I started doing some thinking on my own, which is a big no-no in science land. Oops.
Heritage.
Well, that's what you find out along the way. In the beginning, most of us, and I was too, very naive. Oh my, I found something really cool. I can't wait to share it with everybody, right? We've all been there. And so you become this obnoxious door ringer on other professors and go like, dude, I have something really cool. So, but in the end, you meet or you contact Gerald Pollack from the electric universe, because the electric universe, and that is your question, how did I get there? There were people there like a Gerald Pollack who were talking sense, not nonsense. And now I'm not trying to today to destroy the whole body of mainstream science. That's not my goal. That's not what this is about. But these people were talking sense. They were not afraid to talk about different concepts or different points of view, you know, all supported and based and rooted in reality and science and whatnot. And it struck me, and I contacted him. And the man is a gentleman.
He is.
And he was so kind. And he told me, in very nice words, what you need to do is you need to find other people to talk to. By the way, there's an electric universe. Why don't you take a look at that? But it was in the United States, never been there in my life before. So I packed up my last belongings and shit, and I went to the conference, and I met great people. And there was no result from it for a year. But the first, how do you say that? The first step was made, right? The little stone started rolling from the hill, slowly but gradually, or the snowball, I think, and it started growing. And
That's
so I met people and I started talking to people, and I actually started making progress in my own thinking about nuclear physics, about how is an atom, what is an atom, right? So my very primordial questions were, what's with an atom that makes oxygen an oxygen, a carbon, a uranium? They're always the same. They're always, there's fixed numbers to it. Well, what's the difference there? Just the number of protons and neutrons and some outer electrons? Is that all? How are they organized? I asked myself. And I could find no information about organization because there is none. So, for me, there was suddenly this puzzle in nature, in science, that seemed unresolvable. Well, you got my attention now, right? Now it becomes interesting. Now it's a
right.
challenge. Now it's really cool because I went there and I found great stuff. At least that's what I think. That's what I like to think is my contribution. That is that I have proposed a fixed structure for every type of element out there, including the isotopes with all the nitty-gritty details. Then we started mapping those structures on properties of the elements, right? All the properties that are there, from ionization degrees to the number of the protons, neutrons, electrons, but also the chemical properties in the sense of, on the left in the periodic table, you have the alkaline elements. On the right, you have, the noble,
Acidic.
excuse me, the noble gases, etc. So you have oxidation values. Now there's so much more. And all that stuff started to completely fall out of the model, fall out of the structure. It correlated. So I can show you some more detail on that. But that was my attempt to answer your question there, Matt. So through
Good,
my
good.
curiosity and somewhat boldness and some coincidence, etc., I ended up with the EU people, and I thought it was an excellent crowd with lots of free-thinking people.
Do
And
you,
welcome aboard.
Yeah,
do you remember what year that was that you went to your first EU conference?
2015, I want to say. And
Wow.
that was really my first step. I like to say, I think I pointed it out to you, Ben. There's something and I'm not an expert on it at all, but at some point we did the tarot card thingy, so the past, present, future. It was a little bit jokish, but there was the fool's card there. And the fool's card is a fool journey. And the fool journey sounds really negative, like I'm being the fool, but the fool has some advantages. First off, you opt to play the fool, right? It's not you are a fool. No, you play the fool. And the fool has some advantages. The fool can go everywhere, and the fool can make fun of the king. Everybody will laugh. Now, if a normal citizen would make fun of the king, no matter how much he tried, his head would roll. But the fool gets away with it. The fool can poke his nose everywhere, learn everything, and nobody will pay attention to him because he's just a fool.
And yet,
But
and yet, like all good comedians, what you say as the fool resonates. on a very deep level. That's why comedy works, is because it's a
Comedy has to be,
juxtaposition of crazy, but at its kernel is truth. And that's what
yes,
resonates.
exactly.
It's the number one
So
best weapon against tyranny, in my opinion, or dogma for that matter.
it's
Let's
very
go with dogma.
powerful.
Yeah.
So that's the fool's journey, and the fool's journey is a wonderful journey. It's a journey for yourself to learn all kinds of things. Yes, you will learn a lot of bad things. That's to say, you go to a certain niche, a certain area of information or science or whatever, and that's my experience at least. I found out, ha, we are not that developed. We don't know that much, and we can't explain pretty much anything actually. Sure,
Dark
we have a
age.
lot of technology and whatnot, and that is all really cool. But if we start asking ourselves, do we really understand what's going on in nature, in the cosmos? No, we have some models here that are very limited, quite old, I dare say, kind of like version zero point 0.1, and I think it's time for for version 1.0,
Or
where we have
2.0.
some real science. Yeah, or 2.0, take your pick. The electric universe, by the way, is not the end all and be all. That's not the point here, right?
It's another
The
door.
point in science is an exploration journey. That's the fool's journey. If we already think we know the answer, we skipped the fool's journey. We skipped our homework, right?
Yep,
So
we've
then you
gone
end
straight to
up an
dogma.
MIT professor.
Yeah, that's the beauty of the electric universe is that it doesn't make any illusions about where it all comes from or where it all goes. We're only talking about the things we can verify.
Yeah. If you, and I
Oh,
like to think that if somebody has something to say, the rest of us will be the judge of it, of course, right? And
Yes.
that goes for all of us. But if you
but
feel you have something to say, I feel you should say it. You should speak up in all humbleness and respect and whatnot. But so I was fortunate enough to through people like a Gerald Pollack to get a spot on the stage there with the EU several times, later on in England even. And
that's really
I feel
cool.
like that's really what allowed me to take a little position on the world stage in nuclear physics slowly.
That's awesome.
So I know this. I don't know if Matt knows this, but Ito, you've
Probably not.
been to other conferences that are not EU. You've been to like other nuclear conferences you've told me about. How many of those have you
Correct.
been to?
Oh, slowly losing count now, which is a good thing, I guess. But
Yeah, it is. What was the last
so I
conference that
went
you went to?
to like 4 or 5 electric universe, and I think I went to 4 or 5 um, ICCF, which in a nutshell, it stands for cold fusion slash LENR, low energy nuclear reactions. But cold fusion is the old known term. So I went there bunch of times. They have workshops, so that's more, us and presentations to us. It's. But it is recorded usually and put on the internet as well. And then you have the big one, and the big one is the ICCF conference, so the
That was the one in
International Conference.
Japan?
Well, what they
Where
do is
was
they
that?
rotate over the three continents. So it starts, or it starts, it started in your neck of the woods actually with Pons and Fleischmann. And then a few years later, I think 2 or 3 years later, they started with an actual conference, and then they go to Europe, and then they go to Asia, and then they start over again in the US. And
Wow.
yeah, this is what they keep doing. So last year was in Japan. So next year will be in at least the North American continent. I think it was Niagara Falls that's coming up, but don't hold me to that.
You said it was the
So
ICCF?
that's, yeah.
IC
Fleischman, that guy blew my head.
Ito, did you say it's called the IC? I'm just looking that up right now. You said the ICCF?
The ICCF, yes, sir.
I'm just going to look it up and see where it's at. So in case
If you
anyone
Uh,
add the
listening
term,
and
if you add the term
goes,
Lenner, yeah,
uh,
just Google Lenner and ICCF in one go. It should
got it. Here we go. It is 26th International Conference on Condensed Matter Nuclear Science. Oh no, this is the one.
yeah,
No, this is the one that just happened in Japan.
yeah. Yeah, I'm not sure if there's anything for the next one yet, but the next one will be, I don't know, summer next year, something like that.
Right. Yeah, we don't have a date for it yet. Okay.
No, no, it's not fixed in that sense yet. No, no.
Right. Okay. But
That
anyone
that
anyone can get online and see it. Just type in ICCF and it pops right up. So
Yeah.
that
So that's
Fleischmann
where
guy is incredible. I just have to
what is
put that out.
incredible. I'm so
The
sorry.
the Fleischmann, I think that's his name. I don't know how to pronounce it. That
yeah,
you said
Pons and
you yeah, you turned me on to him, Edo, and I watched some of his stuff. Holy moly, that was mind blowing. The
Yeah.
the space being in the shape of a giant wheel with rings within rings within rings. It's pretty incredible stuff. You've got the ring, and then you have the magnetic field that goes around it. And each one of those is its own circle with the same structure at
Yeah.
45-degree angles all the way down.
me
Yeah. Yeah.
happy.
Yeah. Yeah. So, but yeah, the ICCF, I think that's my forte, right? Nuclear science. I'm the originator, for those that don't know, of the structured atom model, which proposes a structure for the atoms, for every element, a specific structure. It's all based there on logic. There's a book there, there's videos there, there's lots of stuff there. There's a website there that I can show you later on in a bit. I can share my screen, I guess.
Yes,
Well,
please
And
do.
I can
could you
do
give me
that.
a quick breakdown of what the layman might think an atom is if you only listen to the mainstream model, and then contrast it with
Yeah,
yours?
well, give me, I think I can try. I need an example here. I need to find my way
I'm gonna help you,
around.
Edo. I've got my little toys that I can show stuff. So you can
Take it
talk
away,
and
Sparks.
I can walk
Yeah,
you
I just
through
need
it.
to make the right selection here. I think I'm doing that
Oh,
now.
yay. This will be even better.
Oh, good. I
What are
couldn't
you
see your
seeing?
beautiful face up until now. Oh, wait, I
What are
still
you
can't.
seeing?
I'm seeing your
Discord.
screen.
We're seeing the Discord channel.
Yeah, and like a map with a desktop behind it.
That's the wrong one. I don't know
It's
how that
something about
works.
adult friend finder.
Oh my God.
Yeah, yeah, you wish. You wish. How about this one?
Okay, that's not adult friend finder. We're seeing little balls on the screen, little red
Well,
Right,
balls.
right.
technically,
Now
Yeah,
with yellow. So,
it's the structured atom model one.
okay.
You
Bummer.
don't want to talk about little red
Um,
balls anymore?
far more sophisticated kind of small balls.
I'm playing with my
well,
balls.
so what was the question again? Oh yeah, the so currently
Ridiculous.
what we all learn is well, we have atoms and a whole bunch of them called the elements, about 90 or so. There's a long list on the right here, and they are made up. And you can go to any wiki or anything else, protons and neutrons, and on the outside there's electrons zipping around in some kind of Earth orbit, something. Um, so, and then you go like, okay, how does that all work together? Well, the best you can find is some concepts of electron orbitals and whatnot. So that's the outer electron orbital realm. There's some modeling and there's some, computing going on and trying to show how what they look like, but it's just math. And the structure is implemented. So they put their own boundaries there in order to get structure because formulations within quantum mechanics do not allow for a structural component. How are the things organized? It doesn't come up falling out of any formula that calculates forces or chances or whatever. So there is no structure in mainstreaming quantum mechanics. And if you really look at it, it is a topic. It is a serious topic. It's been looked at for a long time and nobody's been able to solve it because we think we need a supercomputer to resolve the so-called n-body problem. So if you have more than 2, 3, 4, 5 particles and they're all interacting with each other forces-wise, it becomes quite difficult to calculate at every point in time where every particle is and whatnot. So that's the quantum mechanics part, the Copenhagen interpretation. A particle, you cannot know its speed and location and stuff like that at the
At the
same
same time.
time.
Right.
Right. No, I
Edo,
think that's quite silly.
can I just pause for just a second and just make one clarification? When you say it's a kind of a mess, what we're talking about and I think what you're talking about, what I want everyone else to know is the nucleus.
Yeah.
Is that the
Yeah,
current
that's what we're
model?
talking about
The current model
in the
just
first
has the
place.
nucleus kind of as just a jumble of protons and neutrons.
Right. Right.
So the
Right.
electron orbits, we do have a pretty good idea of their shape, and they've got some pretty unique shapes which have their own problems to be sure. But when Edo's talking about the jumble and mass of the current theory, we're mostly talking about the nucleus. And this is my nucleus, and you can see it's just a bunch of jumbled balls. So anyway, Edo, go ahead.
Right.
Continue.
Well, even the outer electron realm is just modeling, right? And the shapes that we project on it is simply really our projection. Okay. So
There's
it's
some
not a
problems with it.
resolved thing. Um, so there is really no information about structure. Now, if you try and do it and Google it, there's a little bit, and sometimes people, that's why I have helium-4 here, which is very cool basic element, if you will. But if you start Googling it and you start researching and read papers and see stuff, then sometimes people go like, yeah, 2 protons, 2 neutrons, that's helium-4, yeah. 4 is, of course, the total. 2 protons, 2 neutrons, and then they go like, yeah, that's a tetrahedron, right? I mean, that's a simple one. We can all make a tetrahedron there. It's not in one line, if you will, right?
Right.
So I have something else, I think, ready for that. Can you see this presentation now? Did it change? Yeah.
Yeah, some graphs.
Yeah. Okay. Check. So let me just scroll there.
But they aren't balls, they are magnetic fields we're seeing, right?
No, well, what you're seeing, the sphere, the ball, is simply representing the nucleon, meaning the proton slash neutron. Now, in my mind, there are only protons, but it doesn't matter, right? There's those two equalish protons, neutrons. So if you look at this slide here, this is what we're talking about right now, actually. There's the standard model over here, proton, neutron, or hydrogen-free, tritium, 2 neutrons, right? Or helium-free, 1 neutron, 2 protons. Helium-4, 2. Now, what I say is, no. It's just protons and nuclear electrons. And I have good company, like a Chadwick, at least originally. So, well, this is their model. But, as you can see, there's 2 neutrons sticking together here, right? Or 2 protons sticking together here. But
that doesn't make any sense.
Right, but there's only 2 ways to put free together, free particles, right?
Right.
The linear or the triangular. No matter what you do, those are the only 2 options. Now, there are only 2 isotopes in the whole of nature that have free, and that is hydrogen free and helium free. And that's a linear configuration and a triangular configuration, right? Right, but the problem is when you start growing, you get more and more protons touching each other and more neutrons each other, and of course proton-neutron, right, combination.
Right.
But proton-proton in the mainstream model have this huge, strong Coulomb barrier. And to overcome the Coulomb barrier, you need the strong force to keep them together. And now it becomes quantum mechanics and horribly difficult and horribly complex. And more stuff is implemented, like the quarks. And then you get phonons, resonations, and then you get your antimatter, dark matter, and whatever.
Oh,
and
it's just another
horrible.
Just another stack of ridiculous patches.
So hold on. But it starts where this starts is what's amazing. Edo's talking about all the ridiculous patches, but it started from the strong force. The strong force has never been measured. Why? Because it was a placeholder. It was never.
Fools!
Exactly. It was never a real thing to begin with.
Yeah, it's just like super condensed matter or any of that nonsense.
There are many of these concepts that are considered nowadays like factual truth or established part of science, this and that. That's simply not true.
Yeah, yeah.
It's simply not true.
Dark
So,
matter,
but the
black
thing
holes,
I'm
strong
pointing out is
force.
you get enormous problems with your proton-neutron placement, if you will, the moment you start going a little bit bigger, and you get all kinds of weird problems. Now, that can totally be resolved once you introduce the nuclear electron, the original thinking of how a nucleus is made, what a nucleus is made up of, how it's organized, if you will. But since we never went there, structure has never been resolved. I mean, Copenhagen interpretation pretty much, makes it
Kicked it by the
impossible to
wayside.
even do it.
Hmm.
So for those that don't know,
So,
the Copenhagen interpretation, real quick, is essentially shut up and calculate. Meaning, don't think about what you're doing. Don't think about the meaning of it, whether it has a one-to-one correspondence with reality. Just do the fucking math. That's the
well,
Yeah,
Copenhagen
that is quantum
interpretation.
mechanics in a nutshell. Quantum mechanics, what we're finding out, and this is a glimpse to the future, and has to do with the mass of the neutron in the standard model, which is a problem. There's a huge error there. In the beginning, we did all this stuff and we had a proper concept, and now we're doing it wrong. I forgot your question or your comment there. It's early. I have an apology.
Who, me or Sparks?
Both. I forgot. I lost the track.
Well,
Oh,
I had asked what the difference between the standard atom and your atom is. So
Right.
you
That's
pretty
what we're
well
working on.
explained that pretty well on the Saturn atom, but I don't yet understand a nuclear electron.
Right.
because that's the key point right there.
Well, maybe we can go there. We're jumping around. It's not a full presentation, people. So, lots of detail is missed right now. But
Well, do it your way.
yeah, I'm just thinking.
I mean, the concept
Let's go
is
back.
that electrons exist in the nucleus, and that apparently is not in the standard model. But
In 1933, the neutron was discovered by Chadwick. There was a particle coming out that was not a proton, so not the charge, right? And it was not an electron, and it was very similar to the proton. And it had penetrating power and could cause transmutations and whatnot. And that's the neutron. Now, that is what we call nowadays the free neutron. It can come off in certain reactions.
Hmm.
And that is a thing that I acknowledge, right? That thing exists. Now, is it a fundamental particle? Then I have to say no, 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 because, it automatically decays into a proton and an electron and a little bit of energy.
I, w-
Yeah.
I wonder if that could be the result of what's that effect that kills magnetism under temperature?
the Curie
Curie point.
temperature.
I wonder if that could be some kind of Curie point down at the molecular level that these things lose their magnetism temporarily.
You make me happy. I don't know that
I
we're
don't
talking
know.
necessarily about magnetism as much as we're talking. Well, I think Edo's going to explain it what the neutron is, because you've got a new definition of it.
Right. So Chadwick discovered it and he wrote a paper, and in it he basically calculates the mass of that particle, the new found particle in 1933, right? And he calculates it as the mass being less than a proton, a little bit less, which makes sense as it decays into, it makes sense if you look at the mass defect numbers and the binding energy and whatnot. He understood that the neutron decayed into a proton and an electron, and therefore it was a composite particle, if you will, right? A construct, a little chunk of it, a combination already. And it jived with other observations. And then in 1944, 1 year later, in come the people that were into the upcoming quantum mechanics model and calculations and formulations and whatnot and interpretations. And they started talking about spin and a few other things, totally besides the point. And suddenly a nuclear electron was not wanted because it didn't lead to the proper results. And we're still trying to find out what was actually the problem they had with the nuclear electron and not a neutron. But I do understand, at least that's the preliminary understanding, that it offered or allowed them to further develop quantum mechanics by adopting the neutron concept for whatever particular reason. Yeah.
I don't like.
So that is to be
Yeah.
found out exactly what happened there. But that was the reason for it. And then they started talking about that, and the nuclear electron became a no-no, even though there's a phenomenon such as electron capture. There's a thing that a free neutron decays into a proton and an electron. But we say the neutron is a fundamental particle. That is something that I cannot match in my head. You're stating the impossible, right? Contradictio in termino, if you will. How can a neutron be fundamental if it decays automatically into a proton and an electron?
Exactly.
Now, I know
Yeah,
they go out of their
doesn't make
way
any
to
sense.
explain that to me, but that's no logic.
It's not.
So, the nuclear electron is a charge. Now, we don't know what that is. We don't know what an electron is. We don't know what a proton is. We don't know what charge is. We don't know what mass is. We don't know what light is, right? But we can use other terms here, and that's, I think, good for today.
But we can obviously manipulate them. We can engineer them or use our understanding. But you're right. When it comes to the ontology of it or understanding what it is, you're right. We don't know. But
Well,
that's
Ben,
okay.
did we figure that out on Norm's show? I had asked about the what does a galaxy look like? Isn't it just a large toroidal magnetic field? And if we're looking at atoms, it's kind of the same thing. So maybe that galactic action out of the north and south end of the galaxy represents magnetism.
Maybe I don't.
I
I
don't
don't
think.
remember.
Well, I understand the comparison we make between the smallest and the largest, and it's part of largely due to the fact that somebody at some point equated the nucleus as being the sun, and then the solar system is kind of the electrons around it. Well, I understand it, the comparison, but it pretty much falls flat on its face.
Oh, how so?
Well, first of all, the nucleus, it turns out, is completely static. And the solar system is a moving, turning thing.
Oh, I
Second
would
of
call
all, the electron orbital range would be more the heliopause range. So you're talking a few light years or something like that. I don't know. Big distance, way beyond Pluto. Yeah?
yeah. I was more comparing a galaxy than a solar system.
Oh, right. Well, the same thing. It's moving. And the nucleus, that is my one of the findings, if you will. It's static. Only the static densest pack state, right, is the ground state. That is an explanation already for an energetic ground state. So that's where it starts already. You start explaining things once you adopt structure, and structure does not come out of quantum mechanics, right? All the quantum mechanics formulations, whatever you pick, there is no, oh, right, that's how it's organized, right? Matter, a nucleus. Right. It's not there. So you have to look at charges. So the yellow here, let's do that for a sec. The yellow here represents the inner nuclear electron, right? The electron with the negative charge, we say. And negative and positive doesn't mean a thing, actually. So we say the protons, which are the gray spheres here, they are the nucleons. And we used to say proton and neutrons, but I say only proton. So now I have two different particles, a proton and an electron, instead of a proton and a neutron. But a proton and a neutron cannot stay together. You need a strong force, quantum mechanics, the whole thing. But if you have a negative charge, positive charge, that's not so difficult. If we look at this thing, helium-4, and I'm sure everybody agrees, you cannot crush it further, you cannot reorganize it, it becomes linear, right? It's not dense packed, it doesn't make sense. If you look at the protons, inwardly into its center, if you will, right? If we have just structurally like this, so there's all these protons have half of their visual side pointing towards the center. So that's 4 positive half charges in the center. And outwardly, the other half pointing outwardly, right, is 4 times half a positive charge on the outside. So there's room for 4 times 1/2 is 2 negative charges on the inside. They have to be there, otherwise there's no connection there between the protons. What I think is the case is in the new atomic understanding is there's an electron with the charge that connects to a proton and another proton. And let's go back to the other one. To another proton. It does it 2 times in this case. And it connects the 2 protons. The 2 protons are now interacting. They are now aware of each other, for the lack of a better term. When they are aware of each other, they can do their real magic. And the real magic is when these 2 things fuse, and that is the rule, so that is always the case, when 2 things fuse in atomic physics, out comes energy, right? And that energy is emitted. This can only happen if you have the proper charge there in between connected to both the protons. And that is an equalization, an automatic settling principle, right? Negative charge in the center, 2 positives on the outside, left and right. The positive charges will migrate towards the electron. If you do the calculations, it is enough. Right, so the positive charges repel each other, but there's a negative in between with a shorter distance, and it falls off with the
Simple.
The second.
The distance squared.
Thank you. I'm so sorry. It's not my.
It's okay.
English is not my education in math, so terms, right?
And so that gives it the appearance of being neutral.
Yes, because they equate. So in the center here, right, the charges in towards the center, if you will, they are negating each other. The negating each other is the effect that we see with a free neutron, right? It doesn't appear to be polarized, although it is a little bit apparently. So yeah, so a nucleus is an automatic settling system between charges. They equalize out, if you will, or neutralize, if you will. But on the outside, you keep these half positive charges still that are still not fulfilled, if you will, not negated, not neutralized.
Right. The model that I'm holding in my hand shows this. These are spherical magnets, and I know we're not talking about magnetic forces, but it's a decent model. This, of course, is the North Pole. Red's going to be the South Pole in this story. So what you see here as I rotate it around, the different sides of this helium-4 construct have building sites, and Edo's going to get into this. So this one will obviously take a red pole. That one will take a blue one. That one will take a red. That one could take a blue. Just like that. And that's how you can think of it. That's why the nucleus can grow in specific shapes. And he hasn't really hit on this, but they grow in what's called the densest packing configuration.
Right.
Did I say that right, Edo?
Pretty much, yes, sir.
Please correct me if I said it wrong. Please.
No. It's not about right or wrong. There, it's just a complex story if you go into it. And the problem with this material is it's so novel, it's so different, right?
Yes.
There's not a lot. I believe there's not enough attention to it because the structure reveals so much about nuclear physics and the elements and, in the end, technology and possibilities. But what you can see is there's, of course, in the larger organizations, and this is just quick and dirty here today, yeah? This is all.
And fun.
So what you can see here is just looking at the charges. That's why I like it so much. The blue proton, yellow electron, blue positive, yellow negative. But they negate each other. And you can see, right, every time you have this pair here, and a pair there, and a pair there, and the pair is the deuteron configuration. On the outside is every time the positive part. That's what we call the Coulomb barrier, right? But it's not 12 or 6, in this case, positive charges, and then you add them up in one virtual point. They're all added up in one virtual point because in quantum mechanics, a particle is only a point in space. So yeah, there's no structure there. But in reality, there's half a charge here, half a charge there, half a charge there, half a charge there. And the other side, there's a half a charge there. So a Coulomb barrier, it's not just adding charges. There's a spatial component, right? It matters. Other charges pointing in other directions, right? There's charges in between. There's negating effects.
Right.
So if you look at this here, right, in the center of these three that I'm trying to highlight now, if it's visible,
Yes.
it's very
Yes, it
positive
is.
here. And if it's very positive there, yeah, that's where the next neutron, if you will, the next proton-electron pair, as I like to call them, PEP, can take place. So if you have a carbon-12, well, I can make a carbon-13, right? And it happens in nature. But it's going to be sitting, if you will, on that triangular spot. And there's a bunch of them. There's about 8 of them. And that has to do, and that's one of those characteristics. It's just an example. Carbon can have approximately up to carbon-20, meaning, 8 extra neutrons. And if you add one more, that's called the neutron drip line. It's a very specific research field. Not interesting at all for normal people. But there's a neutron drip line, and then after carbon-20, so you have 8 of those. Do I have that thing? I think I do. Right. It's very cubical, by the way. Super interesting. Now there's no more, options left. There's no more places that I could put the next neutron, if you will. So if I were to put the next neutron there, it immediately departs again. And that's called the neutron drip line. So the neutron immediately, okay, it's cool. I go to the nucleus, right? It can do that. But a carbon-20 says, no, sorry, vacancy full. Yeah?
Right.
Okay. Now, it just happens to coincide with the structured atom model numbers. It happens to coincide with the actual neutron drip lines that we find. This is an example, and there's a long list of these examples. Yet we're getting no attention from mainstream. But hey.
Color me shocked.
Yeah.
Right.
Yeah. And I lost my train of thought where we were. I think we're talking about the difference between the normal and normally the atom and how I perceive it. But there you go.
Well, let me interrupt you one more time for a layman's question. I've said something about magnetism, and you guys kind of gave me the look. But what is holding these things together if it's not magnetism?
That is an excellent question. I believe it is an.
That's a good question.
I've outsmarted the physicists. It's a tiny galaxy.
I don't mean to poo-poo your thinking there. Look, magnetics or electric fields or magnetic fields or electromagnetics together is an extremely important thing, right?
Yeah.
But, however, what I would like to point out is before we get there, right? We have charges. And this is just in my mind. Charge seems to be the most fundamental thing around. Right? So we have 2 particles in my mind, a proton and an electron. That is it. That is the particle zoo. There is only that. Those 2 can negate each other. It's a positive, negative thing, as we say, right? The 2 charges, they want to be together. When they start sorting each other, when that charge, an electron, connects to a proton and another proton, now we have an actual connection between those particles. So the electron seems to be fulfilling the role of connecting the actual one and true particle, the proton. Yeah? Because the electron is very little mass, if mass at all. I think that's debatable even. The bulk of the mass, the real mass stuff, is the proton, and there's only one particle. But in order to keep them together in a nuclear state, so creating the elements, there needs to be a connection between them. The connection is facilitated by the electron. The moment they connect, they have to de-energize in relation to each other in order to be together. That is fusion. That is an observation, right? There's no other way around it. Put 2 of them together, they will give energy. That is fusion that we all talk about. Tritium and deuterium, making helium-4 and a neutron and a bunch of energy. It is important to note here that if you put 2 of them together, and let me find the doodle again. Let me find the deuteron. If we
Maybe
put two
electrons
protons together, or two of these, or two carbons, or two nitrogen 14s together, it doesn't matter, energy comes out. Of course, we have E is mc square, whereby energy is equated to mass and some factor.
So mass is lost as well.
So yeah, it's transferable, is what I'm trying to say, right? They're
Transferable,
interchangeable
sure.
terms in this particular case, right?
Right.
So if I lose energy, I lose mass, and that is exactly what we observe. So if we have one proton mass and another one proton mass, and let's just for convenience forget about the electron just for a moment, right? It should be two masses now, but in reality, I have 1.987 something. I lost a little bit.
You lost a little bit. Exactly.
I lost a little bit of mass, which makes sense because, and we can't see it, there's a little lightning bolt going out there. That's the mass that went away, or the energy that went away, in the form of what we say a photon or a gamma ray.
Right.
So what is binding them together? First, we have the charge, organization, the connection. Then they can come together. That's the magic, if you will. That's when energy comes out. That is that mass defect, that missing mass, that missing energy, is by definition the binding energy. The binding energy, which is, mainstream term here, is therefore the lack or the missing part of energy, right? So
Right.
missing energy is what keeps it together. If I shoot a gamma ray back at it, I give back the energy, I give back the mass, they separate again. This is all standard, normal, real observations, right? I say nothing crazy here. So that is the case. So binding energy is the lack of energy, not something I have to add to it. I have to take it away. In order to stay together, that energy has to be gone. That is an atom. That is an element, right?
And the protons don't lose any mass with this. They still, if they separate and that binding energy goes flying off and you measure each of the protons by themselves, they still have the same mass. Is that right? Or did we lose a little bit even in that?
There's probably a debate to be had there in
Yeah.
scientific communities, but if we look at the mass numbers, actually, proton, neutron, electron, to stick in those mainstream terminology, the proton is, can I put a value to it? Well, I could. Let's say the proton is 1.000. Then the neutron in mainstream is 1.001 or 2 or something like that. Yeah. And the electron is just a tiny little bit, 0.0 whatever, a little bit. It's almost negligible, right?
Sure.
Mm-hmm.
But if we put them together and if we understand the mass is missing, where does that energy come from, right? It comes from the system. Now, we can say, yeah, it's putting stuff together, fields, magnets. Well, you're still stuck with energy conservation, Where does it come from? How does it change? So in my mind, you have a proton, you have another proton, you put them together with the help of the electron, and the proton is the only possible potential source of that mass, of that energy, right? A proton is about 1800 MeV, and I lose about 8 MeV per proton on average, which is what we call the average binding energy. What we also already concluded, the binding energy is the missing mass. The missing mass is per nucleon, expressed per nucleon, right? As binding energy per nucleon. So 8 MeV per nucleon is what we say is an optimal. That's iron, nickel, cobalt, that optimum thing. Below it, they say, only fusion. Above it, we get the fission. It's such a limited, erroneous point of view. It's not even funny. Fission always works. It always yields energy.
Yeah.
So let me stop
Fusion.
and divert here for a second. I had a question a little while ago that what is the difference between radioactive decay and fission? Because when you look it up, they're the same thing. And so what I discovered, what I
I'm sorry, what is
understood,
the same thing? What you looked up? What is the
fission,
same?
fission, which is what we associate with bombs, hydrogen bombs, just a
Right.
huge amount of energy, and radioactive decay. I was like, what is the difference between those two? The same thing is happening. You're getting a split up of the nucleus. That's what radioactive decay is. That's what fissioning is. So what's the difference? And what I
Well,
came to understand, and you can tell me if you think this is right, fissioning, like what happens in bombs, is radioactive decay happening billions and trillions of times all at the same time. Whereas radioactive decay is the splitting of the nucleus a little bit here, a little bit here. It's happening very, very slowly. Is that a good way of understanding it?
whew, fission. So fusion is putting stuff together. Fission is
Fusion's putting stuff
breaking it
together,
apart. Yeah.
fission's breaking it apart. But
Yeah.
that's the same thing as radioactive decay.
No, that's not. So let me correct you there.
Please,
This
go ahead.
what we're looking at here, if you can still see my screen there with,
Yeah, we can.
in this case, lots of uranium stuff and whatnot.
Yeah.
Yeah.
So we have uranium, that's the fission. It breaks up, little arrows there, right? It breaks up in barium and zirconium, and that's just an example. Yeah, these are example products. There's a spread of products, right? And here you can see it together. A uranium breaks up in 3 chunks, but 2 chunks actually come together. That's why they break off at the base. And yeah, well, can we see it? Well, it's
Yeah, we
not
can see
really
it.
visible, but 2 come together by adding one more particle. 2 branches kind of fuse together and make a new core, if you will. And it has to snap at the bottom due to having a different angle then. And then you get an electron reconnection, and then poof, you suddenly have effectively 2 nuclei stuck together, where suddenly all those protons are pointing at each other, and then poof, it splits apart automatically, right? Cool nature. So that's fission. If you're talking, and fusion we went through a little bit. If you're talking radioactive decay, right, with a nuclear bomb or a power plant, then we get
Fission.
gamma rays, neutrons, and all that stuff. But if I tell you, and you can go to wiki, everybody can go there and read up on this stuff. It's all there, right? A blast, you get a lot of electrons and a lot of photons, light. The radioactivity predominantly comes from all those isotopes that were created. Let me go here. It's like the barium and the zirconium and the da 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 da. And they are not okay because, a whole chunk flew off and it has to reorganize a little bit in order to be okay again. So that is a normal decay step. That's beta decay. Where's the beta decay? Like this. So, for example, a neon 23 or sodium 22, this one has one too much, this one has one too little to be in the proper state of that particular element. So it has to reorganize, and these are just 2 simple steps, right? But this is what happens.
And what you're trying to say is the reorganization process gives off energy, and that is the radioactive decay. Is that what you're trying to say here?
The reorganization has to do with an electron, beta decay, going in or out, right? So beta minus decay, you get an electron in the outside extra. A beta plus decay, an electron on the outside, an outer electron goes into the nucleus, electron capture, if you will, right? So in the particular first case, neon 23, we have 3 of those light-colored yellow-greenish ones. Those are the aka the between brackets neutrons, but one has to turn into a proton. Neon has where are we 10 protons, 10 neutrons, and the sodium has 11 protons, right? So one changes into a proton, so it becomes a sodium, properly organized. Take away one, the other way around, you get,
But
it has to turn a proton into a neutron. So it captures the outer electron, beta plus. That is the beta decay. In this process, this is where the gamma rays come from. Because an outer electron goes to the inside. Remember, we learned, or stated at least, that the electron connects to two protons. And if an electron, if we change something, yeah, we did something, it has to resettle. That means maybe reconnect. And the reconnection is when the two protons are connected. That's when the energy comes off, if there is energy needs to be shedded, like with the fusion steps, right? And that energy comes out of it. That's the gamma ray. That's when a gamma ray occurs. Only then. So at the fission process, that's not where the gamma rays are produced initially. So in the Lenner, to bring it back, if I may, Ben, to bring it back to Lenner, cold fusion, we're not seeing really lots of gamma rays, but we do see excess heat. We're not seeing really neutrons, but we do see excess heat and transmutations. And all the mainstream scientists, they lose their mind. It's not possible. Coulomb barrier. This cannot be. You must have made mistakes and whatnot. And I keep trying to point out that we have more than quantum mechanics. We have now structure. It is utterly critically important. Quantum mechanics should be, or was originally, the study of the interaction of particles in between them, right? The forces and whatnot in between. So tell me, what am I doing here? Now, everybody may criticize me to no end or destroy my work if they can, no problem. But this is what we're doing, right? This is the research topic, and we're finding great, great stuff.
right. Let's talk about that for a second. You wrote a book. I have that book.
Yeah.
Reading the book. You have 3 other authors in that book. Where did you meet them?
Electric Universe conferences, of course.
Well, so tell us about everybody that you met there. You met James, and I'm trying to remember the names of the other 2 gentlemen that you wrote your book with.
Okay. Quick reference. I came back in 2016 after 2015 because by then, after my first year, I was talking to a few people, and there were a bunch of those crazy fellow countrymen of yours and male, female, and they were going like, "What you're doing there is pretty cool, and maybe you should do a presentation in a breakout room, right, on the side, right? Just a tryout, if you will, right? Let's
Right.
see if there's something there." Well, that materialized, so I was super nervous and all that. And they helped me. I was financially ruined back then, and they helped me out.
Oh, that's
So
cool.
we worked on it, and we got a ticket, and then the conference fee was waived. That kind of stuff. People put me up there, and where Mark Span needs to be named here. Mark Span, a man behind the scenes who made a lot possible, and he organized the geology tour in, now help me out here. That's New Mexico, Utah, Nevada. I think it was the round trip, more or less,
Did
sort of.
Mark do it? I thought, yes, I know the one that y'all went on.
Yeah,
Yeah,
so
Robert
that was
Hawthorne talks about it quite a bit.
amazing. That was amazing, where we looked at all the electric features of, the Earth that we state is going on there. Andy Hall talks all about it. For those
He
that don't
does.
know, look at it. It's amazing stuff. We had a great tour there. So we had a bunch of cars and a big van and a bunch of people,
Right.
like 20 people or so, in way too hot weather. And we're talking 50 degrees Celsius. So that's 120 Fahrenheit or something like that.
It's pretty hot.
Ooh.
It's pretty hot.
No, it was record weather for the whole week. So I don't understand it nowadays. We seem to be cooking the earth, but hey, it was really hot. And we went there for a week, and I hopped in different cars with different people when we were going to the next location. You talk to people, you meet people. And I hopped in the car with this guy, James Sorensen. I kind of resonated with him. He was a little bit laid back and, oh, cool dude. And we're talking, and I'm inquisitive, so I started, oh, what do you do? And he was driving. He goes, I'm coding, and I'm looking for a new job, something with three-dimensional in science, and I want to code stuff. And I go like, huh? I'm looking for a dude that can code me what we're looking at right here, right? This whole program here of how all this is built together, and I can build these things with rules that I determined. And I looked at the guy and I said, well, I need a coder to do some three-dimensional organization, da 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 da. And he was driving. He looks back for a few seconds. That you dare just that few seconds as a driver, and
Yeah.
he looks at me kind of like you're joking. You're messing around with me here, right? Because it was kind of like perfect match. Just a random
Just a
meet.
random, yeah, the two
Yeah, and
pieces
it's
of the
kind of
puzzle
like, yeah,
come
I'm looking
together.
for that employee, and the employee goes like, I'm looking for that employer, and we go like, match. So that happened.
It's weird.
So I
It's
came
weird.
back later on, a few months later, I came back again to the US, but this time to James Sorensen. We locked ourselves up in the cabin in his cabin in the mountains in Colorado somewhere. And we started working, and that's what we're looking at. That's the result. So that's James
Oh,
Sorensen.
cool.
Then I also met Jan Emming, same tour, and Andreas Otte, same tour.
There they are.
And Jan Emming is originally a Dutch citizen long ago, but became American long ago. And he's excellent in scientific language, writing and whatnot, and EU enthusiast and translator. So he popped up in my circle and made a strong connection there, and who was critical in all the writing efforts and whatnot. And then Andreas Otte, German guy, EU enthusiast, was way back when already connected to, help me out here, the guy that was the tour about, we spread his ashes. Michael,
Armstrong?
no,
Not Michael Armstrong.
Steinbach?
Oh,
Steinbacher?
Steinbacher.
Right? Am I
Oh,
saying it right now?
yeah,
I'm so sorry.
yeah, Steinbacher.
Michael Steinbacher, yeah, that
Yeah,
was him. He was the pioneer there, right? In the sedimentation layers and whatnot with the Grand Canyon and all that.
he did. He
And
did talk
Andreas
a lot
Otto
about.
was connected to him. Sorry?
Yeah, I've seen a few of his Thunderbolts.
Yeah. So Andreas Otto, smart cookie, I made a real connection there, but it didn't lead to directly to any kind of cooperation. We knew each other for a couple of years, but slowly we started communicating, and he started thinking along and helping me out a little bit. And turns out he became kind of like the my secondant, or how do you say that? He's the most into the structured atom model details now that I can say. Of course, the other two are really good as well. James coded all this stuff, so he knows pretty much all the detail. But a little bit more scientifically speaking, Andreas Otto would be a little bit stronger, right? So
Okay.
they both have their part to play here. So that's the whole team, if you will. Well, there's other people that we communicate and talk to and work with, but that's the S.A.M team as it was that created the book. Where is it? Here, here's
There
the
it
book
is.
cover. Yeah, it's for
Mine,
sale everywhere.
mine's upstairs on my nightstand table with all the other books that I read.
So
The
that's
Nature
how
of
it
the
could
Atom.
say again.
Yeah.
Oh, I was just
So,
reading the title.
Edo, how was the book received in the scientific community?
That's a trick question, I guess. The
Yeah.
scientific community. Let's see. What book? What?
Yeah.
No, it's for the individual person, of course, to like it or not, buy it or not. We're not interested so much in, oh, we want to sell as many books as possible, right? We try to nail down what we had because it is a work in progress. I'm sure everybody can understand that in order to every topic that you talk about here opens a whole can of worms in, mainstream physics and whatnot.
Mhm.
Chemistry, cosmology, everything. You touch everything there. So, and that's why
We offend everyone.
Yeah, I saw he
Equal
fits all that
opportunity
well. Yeah,
offenders.
yeah, yeah.
Okay, so
Um,
let me that brings me something I want to ask you specifically about this. In the book, what do you think is the number one thing, if you were to make a list, that is wrong with the current model? Is it the nature of the neutron? Is it the densest packing? Is it what is it? What's the like the number one thing you think is wrong with the standard model?
interpretation.
We could say that with everything. So let's drill down on the interpretation of what?
One of the most fundamental things is the Copenhagen interpretation, whereby, particles, you cannot know its speed or location at the same time, or no, let me go back. Antimatter.
Antimatter. Okay.
Beta decay. Let's go back there. That's a
Not
good
that no, I
example.
don't think those are the same thing, but
Well, here's the thing. Mainstream says that, where is it?
yeah, what's a B plus decay?
Well, okay, this one, sodium 22. 11 protons, therefore 11 outer electrons. Yeah?
Yeah.
Okay. Goes to neon 22. 10 protons, 10 outer electrons, one less outer electron. The electron went into the nucleus. What does mainstream say? No, 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 no. In came a positron, annihilated with the electron.
Oh, boo.
Right.
Can you show everybody on the map on the viewer where you think that electron goes to?
Oh, yeah. Well,
I would like to see that because that's critical. Because if the mainstream says that a positron comes in during that decay process, I'd be like, that is one hell of a lucky positron to just be flying throughout the universe and say, oh, hey, I just found my mate. Kablam.
right, right, right,
It's
right.
a little weird.
It's a little weird. But if you have an extra electron that doesn't want to hang around, he's going to go right, and you're going to show us right here.
I wish I could show you animations. That is on my wish list to have a far better builder, if you 2.0, if you will, that would allow to show the answer to your question, if you will, right?
Sure.
But just quick and dirty. So you're looking at the workshop here, everybody. This is the workshop, right? Not a cool presentation.
Right.
This is the sodium. Sodium has this red construct on the left, which is like lithium. So that's why it's red. It's recurring. It's a recurring structural organization, right?
Which is a really cool thing on its own. If anybody gets on
Right,
this
right, right,
website
right,
and it scrolls around, you're going to see that reoccurring floret pattern
right.
over and over and over, which is really
And that's
critical. But
important.
that electron's
That's an
going where?
important
In that
finding, yes.
valley?
So let's go to this is the normal sodium. This is how sodium should be and is. Now, we've done stuff, we're doing nuclear physics. We take away a neutron there, right? We bombard it and we knock it off. Now you have a sodium 22, which decays with a gamma ray with a beta decay step. So the beta decay step we have here, sodium 22 goes to neon 22. On this one that I'm highlighting, purplish, let's say this pair here is a neutron and a proton, right? These are the conventional terms. I use only proton, but that's not the case. This proton needs to go over there and stick to that position. But in order to do that, it needs an electron to stay there.
So it goes right
Right?
there in that gap. Okay.
How's the electron go
So,
there?
right. So going back here, that one that I'm pointing at is a proton, not the neutron, conventional terms. It
Is it a pep?
migrates to the other side because that's where a negative charge can land with all the positives there. And the proton is pulled in, if you will, to the left. Now it's denser packed, more optimally packed, more denser packed, shorter lines, if you will, or more connection lines. hence more energy emitted, hence lower ground state, hence this is the direction of the automatic decay. But it does need a nudge, but that's a different topic. So the electron, one electron from the outside is pulled in order to facilitate that change. Now they say that can be either electron capture, and then they don't talk about where the electron went.
Where the electron came from, exactly.
No, where the electron went to? It went into the nucleus. No, oh no, it's not there. Wait a minute. Or, as normally is stated, we have, or at least emphasized and pointed out and highlighted, we have a positron that annihilate da 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 da. So my question, sarcasm, irony dripping heavily.
Yeah.
Where is the positron hiding in the antimatter realm
exactly
to know exactly when and where to appear in order to annihilate with that electron?
I'm a positron.
You look like a positron.
It's ridiculous.
I show up whenever I'm needed.
We don't need antimatter to explain anything. You do need antimatter to do quantum mechanics.
That's and as Walt Thornhill has told us repeatedly, antimatter is not a thing.
It's not a thing. It doesn't exist. It's BS.
It is incredible how much is in the mainstream models that doesn't exist. There are a lot of patches.
And a lot of placeholders that have evolved into being thought of as real things. It's incredible.
Right.
Yeah, it's crazy that we treat these people like the experts.
Well,
just making stuff up.
They make stuff up.
Well, it's such a double-edged sword here, yeah?
It kind of is.
Because they are intelligent, smart, heavily educated people that can do and understand a lot. But the models and the thinking has become so polluted after 3 generations that you can't make sense of it anymore. If you keep building error on error or misinterpretation on a misinterpretation, even if so slightly every time, you end up with complete garbage. That is to say, you have no understanding, yeah? Maybe you can do some calculations that are more or less roughly approaching, what we observe. But that is not even true. I can point out so many problems. The tritium and the carbon-14 decay, automatic decay, they are radioactive isotopes. They don't make sense in the mainstream interpretation and calculations at all. They are enigmas because what we're talking about here, remember, energy conservation, E is mc squared, has to fit exactly. You can't create or destroy energy, right?
Right.
So in these automatic decay steps, like a tritium, let's go to tritium quickly, and carbon-14, for example, this one decays into this one. But if they do the mass/energy calculations, you find, it should be completely different value than what we observe. So in carbon-14 and nitrogen.
So they make up another story.
Well, yeah. So this one too. This one is carbon-14, very well-known one, right? For the dating stuff. Goes to nitrogen-14. But energetically, mass-wise, it should be different, and it's countercurrent and actually, than what we observe. And we're talking, what we should see is like, I don't know, 0.7 MeV difference. I think I'm doing this from the top of my mind now. But in reality, we see 16 keV. So 16,000 versus 700,000 or something akin.
That's not even close.
The numbers wrong here.
It's not even close.
And so what I'm saying is, the calculation that we boast about, right, is all so precise and accurate. And then we look at this decay step and we go like, they shouldn't even decay. It's countercurrent. And when it decays, it's 16 keV. It's not even the number close to what we're calculating. And it's the wrong side. It's negative instead of positive, right? So how can it even decay? Well, there's an error in the determination of the mass of the neutron.
I'm going to see that in my dreams.
I'm a positron. I'm here to fix all your problems.
No, no, Marvin. No.
Well, if the electron goes into the nucleus, electron capture. But you do not acknowledge electrons within the nucleus, but only neutrons that decay into a proton and an electron. But the electron is not there, right? Then you have to whisk it away. You have to magically make it disappear. Well, that's your positron. And we can talk all about this very long. But the moment you start talking about this utterly most complex topic, and you start thinking it in some more simplistic terminology, not wrong, people from MIT, etc., not because we don't understand, or etc., we don't understand your math. That is correct. But we fully understand what you're doing there and your concept. But they overload us with all kinds of terminology. I've seen pieces
And
of
equations.
text. You can't read it. You can't read it. You have 4 or 5 completely specific, weird terminologies that imply a boatload of things, like strong force. It is a placeholder. Let me go there, Matt. You pointed it out. I think Matt pointed it out. Strong force. It is a placeholder, right? Well,
Placeholder.
the strong
Absolutely.
force allegedly has only a range of, what is it, like 6 femtometers. And if you understand that the radius of one of these spheres is about a femtometer, or 2 femtometers, I think. So it's about 3 times the radius of a proton, 3 times. But conveniently, lo and behold, the size of a proton, or its influence sphere, in the conventional terminology, is about 2.8 femtometers in radius.
I'm a femtometer.
Oh.
You asked.
So
I
know,
asked.
it's ridiculous.
So the range of the strong force, right, is approximately the size of what we know is the electron. Coincidentally. So an electron on this side of the nucleus does not connect to the protons on the other side of the nucleus. It only has a limited range. That is jiving with what we know and what we observe. But we can't go to the electrons in the nucleus for reasons I do not fully understand. And that happened in, the 30s previous century.
I think what's going on here is that mathematicians are very brilliant, but they're terrible at imagination. And so when they get to things they don't quite understand, they're not good at world building, so they build stupid worlds that don't make any sense. Like,
Well,
You may be right.
you need people that can visualize big picture. You know what I mean? How things fit together.
Sure.
And it's like you've got in mainstream a bunch of people that feel like they've got a good idea how the little parts work, but when you expand it out, none of the stuff works together. It's like there's a big picture view missing.
There's that, and it's a very complex problem. The other thing is that the nice thing with math is that you can solve problems that don't have any correlation with reality. In logic,
like calculating Superman versus the Hulk.
You
can
can
be
do
done
that
with physics.
Yes, you can literally create an equation that will solve for that. That, you can make the Hulk stronger, or Superman stronger, and it will be cogent, is what it's called. It is internally correct, but it doesn't make any sense in real life. And that is one of the main things that's happened with the standard models. We have all these equations which are logically internally consistent.
So elegant.
And they kind of agree with reality and measurement, but they don't really. And sometimes they're completely nonsensical, like strong force, like Edo was saying, like, it's femtometers. But we know that the electric charge of these proton-electron pairs within the nucleus, that influence is felt all around it. That's what allows another proton-electron pair to go find it, wander around and go, I'll click on here. That could never work with the strong force. It's not strong enough.
Yeah. So to broach one more time into unscientific woo, because of the quote, as above, so below, let's pretend that atoms are galaxies. Wouldn't a good placeholder for the electron be a Birkeland current that connects the galaxies together?
I'm thinking.
I mean, because we don't really know what these dots look like. We can only see so far down.
I think the comparison is not correct in that sense that a Birkeland current is like an electron, but the Birkeland current does fulfill probably the same role as an electron, meaning it connects two objects charge-wise, and energy can flow between them.
Also,
right. So in that sense, Matt, I find your comparison very apt. I think.
But there's more than just that, because when a star captures another star, what do? You get a solar flare, where one star bursts off into a giant blast of energy, right?
So I repeat,
Fusion?
Putting things together
Fission?
yields energy into free space, and the system lost that energy or mass.
Yeah, and
that seems to be the case at every level.
But all those stars giving off electrons, right? In the interstellar space, Steve was saying that it was like you would get fried if you went into interstellar space because it's so electron dense, and that we live in these pressurized bubbles, basically, that are the heliosphere of our stars. And those electrons from that pressure bubble are coming through and being sucked into the star. That's the electric potential between the heliosphere and the star at the center, right?
I vote yes.
That kind of sounds like the same process, but just.
Well, that's I think what you pointed out there is actually quite crucial. If we understand that putting two masses together yields that energy, there's an underlying drive, if you will, super fundamental here, right?
Yeah.
So I think that's. So here's how I think and work. This stuff that I try to create it, if you will, it doesn't come like, you're sitting there, that's cool, right? That'll fit. No. I can be stuck for months or longer. Time is irrelevant here, on just one simple little piece of awareness, like what Matt just pointed out. Putting things together yields that energy on every level, it seems. That is such a crucial thing. That can be the starting point of completely new redoing the physics and understanding of cosmology, if you understand what I'm saying here.
Yes.
But you're not going to do it in 10 minutes.
Yeah?
It depends on your focus and how much focus you put into it. That's the hard work. That's the monk's work, right? Days and days of writing in that book. And maybe next week I'll be at the bottom of the page, right? If I really keep working at it. That's the level of work that needs to be done in fundamental physics. Yeah, and like you said, they don't have much imagination, because what I caught them on so many times in everybody that deals with structure a little bit even, right? Take a flat tabletop like my desk here. I take these marbles, which they do too, virtually or not, and I start putting them in layers on the flat, two-dimensional tabletop. And then they go to the realm of 3 dimensions and go like, yeah, but in the real world, then it works like this and that with layers built on a flat tabletop. Wait a minute, you can't even imagine a 3-dimensional space and start from that. That's where I started. That's the difference. You can't do 2 dimensions in a 3-dimensional world. So all of them start with layers on layers and whatnot. The first step they can do, that's the tetrahedron, and show it in that form. Sometimes they find, well, the icosahedron with 12, that could be carbon, right? That could be. But then all the others, it don't match, it don't work, and it especially won't work since the neutron mass is wrong. So every time they try it, they go, it's wrong. Yeah, it's wrong. Just to show you back to the strong force range, right?
Oh,
what I'm playing here with is the size of the electron. Now, we don't know what's going on in that nucleus. There are so many questions here still, yeah?
Yeah.
But
Probably.
this would be
Yes.
size 1. This would be the electron is just as big as the proton. The proton is zero 0.8 femtometers or so in radius. That's 1.67 femtometers in diameter. If I make the electron, which is about 2.8 femtometers radius, I think, right? So about 3 times the size of a proton, which is this, I envelop the entire nucleus completely. Yeah?
Uh, uh,
Right?
right.
The nucleus, however, is positively charged 12, negatively charged 6, 12 half positive charges sticking out, which I'm trying to, mimic here more or less, right? So there's your Coulomb barrier visualized for the first time. The
Wow,
blue is
that's
the
pretty
Coulomb.
cool.
Now, where do the outer electrons go? Well, the outer electron wants to go, here or so, but you can't come close. The
And
outer
that's why,
electron cannot connect like the inner electron to a proton.
Oh.
right. And
So
that is
that's the cool.
that's the simple reason why electrons in orbit, or orbitals to be technically correct, don't spiral into the nucleus. There's already a negative field there repelling them. So yes,
It
they're
works the
attracted by the protons, but they get close enough, and all of a sudden you get that Coulomb barrier around the nucleus, and they're like, nope, we don't want to go further in anymore. It's
There's more
simple.
charge.
Simple.
So the outer electrons, the 6 ones, would love to go also towards the protons. But the other inner electrons have connected to the protons and are large enough in their influence sphere to project all that negative energy around that positiveness. The outer electron is, of course, attracted to the nucleus by 6 positive charges in total. That is what we know as the electron, the outer electron energetic, if you ionize it, right? The ionization energy. You need that much energy to knock off an outer electron.
Yes.
The outer electron is not truly connected to the nucleus as the inner electrons are. That is a key difference between the state of that electron. It is either in the nuclear inner state or in the outer electron state.
Right.
There's a difference. The outer electrons are electrostatically attracted. Yes, that's exactly what we observe, see, and can calculate. But it cannot come close. It has to stay at a distance, and yet it is attracted. So you can reshuffle, reorganize them, knock them off quite easily in relation to where they would be if that close. Yeah, if they were that
Right.
close, it would be much higher energy levels. So this is completely logical.
Yeah.
It's logical.
It's logical.
And that's all I can point out. I cannot convince anybody, but whatever. But so this is the nature. That's why the book is called The Nature of the Atom.
Nature of the
It is
atom.
different. It is not a proton and a neutron and a mysterious force keeping them together. Because how are you going to which one is the neutron? Which one is the proton, please? Why is there a neutron here and a proton there? Or is there no organization? Is it just a chaotic ball? Why are the outer electrons organized in electron orbitals, right? If there is no underlying structure to dictate that outer orbital organization.
Exactly.
So,
And we've measured that.
yeah.
We have measured.
Even a child could understand.
Even a
Say
child.
again, please.
It's so
Yes,
simple.
sir. If you cannot explain the most difficult stuff, at least in simplistic terms, which is exactly what we're trying here today, right? We're trying to that childish inquisitiveness, and understanding. You need to be able to understand it in simple terms. What do they say? Well, we have a lattice with more difficult terms there, and then those lattices vibrate, and that's boson, phonon, vibration, lattice, da 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 da, and then electron screening. It becomes completely impossible because every term, like I said, requires a book. You need to know about that dude who invented that model with that force, which, like you said, it has no bearing in reality. But you need to know all that to even understand what they're talking about. And then
It's
comes
like second
all
edition
the math.
D&D. Every rule has its own thing.
Right.
Well, the mainstream is more like a redheaded stepchild. We have to beat them repeatedly.
Ouch.
Well, allow me to say this. Look, mainstream is it's too simplistic, yeah? We have a lot of good knowledge. We have a lot of good data. I usually argue we have a lot of good technology, but it doesn't mean we really understand what we're doing, right? But there's a boatload of people out there in every field that are really good people, really good scientists, really good experimentalists, really good theorists, etc. The problem is that we're teaching one universal truth over all the universities all over the earth. You can't deviate from it because it basically is a threat to their prestige and position and power and money and whatnot. I'm sorry, but that's what it comes down to. So the individuals usually have a lot of scientific, inquisitiveness, curiosity. They want to know, they want to understand, they want to go there. But it's collectively like the crabs in a barrel, right? The one starts climbing out. Look, I can
Come
see a
back
little
down.
bit
Come
more.
back down. Exactly.
And you're cut into, they cut off your limbs and you fall down.
That's a
Never
good
to
analogy.
go up again.
It
And
is.
that is the reality in scientific land. There are so many people that are destroyed in their career. Well, they should be celebrated. There's something toxic going on there. Because science became, what was the term again? Science is settled. Well, yes, sir. Science is settled in the sense that it is an inquiry into finding out things. It is, an investigation. It is not a settled factual thing,
Yeah.
ever.
So,
And all these political people, oh, science is settled. No, regardless of the topic. No, science is not settled. That's an idiotic statement to make.
right.
Yeah, we don't know shit.
So let me we've been talking an hour and a half now, and my head's about to explode. I don't know about you guys. I need to rest this because we're coming off. Matt and I are coming off. Actually, what everyone doesn't know, 2 other hours talking with Edo yesterday. So my head's like boom. But let me leave you with this. I want to leave everyone with hope because we've really poked holes in the mainstream model. But there is a Nobel Prize scientist named Albert St. Georgi, and he has a quote, and I have it printed right over here on a little placard in my lab. And I think it kind of sums up what Edo has done. Because Edo, you weren't really in the mainstream. You were kind of on the outside looking in and saw stuff and said, hey, I think it goes like this. Listen to this quote by Albert St. Georgi. He says, scientific discovery consists of seeing what everyone else has seen, but thinking what nobody else has thought.
Huh.
Tell me that doesn't exactly describe the S.A.M model.
Yeah, well, that's kind of the way I explain it. Like, it's not so much the facts or the experiments or the observations that are different, because that's why I often or sometimes have difficulty understanding why I'm even on the outside, if you will, right? I fully understand, but why it's difficult because
We do.
I look at the same data, I talk about the same nuclear reactions, right? It's all very close. It's a few different terms, but it's a different way of thinking. It's a different way of looking at it. It's a different, like I said in the beginning when I corrected myself, the main problem is interpretation. I guess I was referring to that already.
And there we
And then
come
I
full
chose
circle.
the antimatter as the prime
Edo-
example.
Edo, are you an artist at all?
A what?
Artist? You have artistic talents?
I'm afraid that is an underdeveloped side of myself.
Why do you ask, Matt?
I suspect artistic people are good at seeing things as they are rather than how they're presented. And so I just wondered if Edo might be an artistic type person.
He might have that varied
I
talent.
think I have some latent underdeveloped potential avenues to explore there in trying to answer your question. I feel I do have some artistic stuff, but I am not a musician. I am a musical. I
Mhm.
love music like everybody else. I can recognize tone and good stuff or bad stuff like everybody else. But letting me play that's kind of like not gonna be it. So that's not my thing. But I do like, for example, in my youth, I like to draw. You know,
Oh,
Well,
you
there you
do?
go.
Oh, well,
That's what I'm
there you
talking
go.
about.
Yeah.
drawing. I
I'm an
I still
illustrator
draw
as well.
sketch.
Yeah.
I still sketch. Pencil, paper, sketch.
That's exactly what I'm talking about. More so than music, people that draw have a ability to see things
Right.
I
exactly
agree.
as they are. Mhm.
Okay. So
I
maybe I
agree.
gave away too much there, but yeah. So maybe that's
We
yeah.
gotcha. All
So
right,
he
man.
is.
Thank you so much. That was
Yes.
fascinating.
Thank you
Well,
very
I really hope, I do hope that those that do listen to this, and especially this one, that it wasn't too chaotic. And it's such a big topic to put into one conversation because there's so much that we can go into. And perhaps in the future we can go into more how do you say that? Specific,
Specificity.
specificity.
and
Okay, breaking my tongue
Specificity.
here. Not going to try again.
then
That one.
when this comes out, make sure and visit it and look at the comment section. Because I'll do this again. I encourage people, if they have a question specifically for Edo, leave it in the comments,
Right.
Hmm.
and then we'll have Edo. I'll prod him to go and see if he can answer those.
Yeah,
Right.
and if you want to see some more stuff, there's
There
stuff
it
to be
is.
found on the website,
Tell
and
everybody the website name.
you can even view all the atoms like this. Everybody can view them. You can run through it.
Oh, show me a regular carbon atom.
You have, I mean, it's no use, but you can just see it. This is
I heard,
carbon. There's your
I've
carbon.
heard it described as 6 protons, 6 neutrons, and 6 electrons, which of course that
Yeah,
can't be accurate. But are there 18 elements of some sort in it?
I'd like to describe it as 6 deuteron pairs with 6 inner electrons and 6 outer electrons and 12 protons in total.
And
I just call it pretty.
we're made of carbon atoms, which is
Yeah.
six six
Well,
six.
let me throw on this one a little bit more political sensitive as my final comment
No,
there.
don't fill it. No, not politics.
Are we going into politics?
No, no.
No, that.
Oh, all right.
And I already forgot my train of thought there. What was you were alluding to something there? Oh, no, what was it? Never mind.
Yeah.
I was asking about the carbon atom, if that helps.
Okay. The carbon atom is locked up in CO2. CO2 is used by plants to do photosynthesis.
Mhm.
Photosynthesis is used by plants to make the simple sugar ring or sugar. That is the most fundamental molecule that is used for almost every biological construction that you can think of, meaning our bodies, our cells, etc. The DNA, the RNA, yada, yada, yada. Sure, there's other stuff coming into it, but that is the basis.
That's awesome.
That is the basis. So water and CO2 make life. And we go around bombarding CO2, the most fundamental building block for life, as a pollutant.
I know, it's so stupid.
So reconsider, people. That is
Oh
a different
no,
way of
plants
looking
and
at
animals
things
are going to
too.
have lots of extra verdant. It's so stupid.
That's as far as I will go.
All right.
It's just stupid. Okay, so next time we do this, maybe we'll let Edo and Matt go off on a political rant.
Nah, no.
I like the idea of a drinking game where whoever gets mad has to take a swig. I don't drink, so it would be really interesting, really fast.
That would.
I rather talk about how are we going to use this kind of knowledge within an electric universe group setting, if you will. We need to get back to electric universe conferences with topics like this, but also work from an Andy Hall, for example. Right?
Yeah.
Exactly.
And we need cosmologically new people to do some amazing stuff there. Matt, you made an excellent observation today. Galaxies kind of connected together in energy coming off. Maybe there's something to it, right? But we need to
Maybe.
continue exploring this because mainstream is not going to change on its own.
No, we got to laugh them out of existence.
Or slap them.
Silence!
I think, well, personally, I don't even want to fight them. I don't want to debate them. I only want to talk to the people that feel, okay, there's something there. Let's talk about it. Even if we're wrong or crazy in the end, let us see what comes out of it. I don't think we're crazy.
Yeah, why not?
I don't
Man,
think we're wrong.
Every batch of experts in the history of the world has been wrong. But
Yeah.
we all build a little closer to the truth. So
Get a little step at a time. Exactly.
Mm-hmm.
But if you stick to the truth, it's a very slow process, but you can actually build a decent foundation that is at least truthful.
Yes.
I'm not saying everything I say can be, it's not like I'm trying to be the oracle of truth here. I'm not even implying that I have an answer to all these questions. No, but not by a long shot. But what I do say is we can understand the atom, the nucleus, which makes up our entire reality in every way, and we ignore it. We ignore the atom. We ignore how it's functioning. Well, ignore it. It's not true. But we're doing a lot of things wrong for other reasons, and we need to continue with the proper thinking and the proper progress of the scientific exploration that we have, and simply ignore the stupidity that comes from the mainstream. Again, mainstream is not all stupid, people. There's a lot of good stuff there, but the models are wrong, and it's time to ditch them. And I think the electric universe is, paving the way here. So, yeah, let's continue.
Well, thank you, Edo, for your amazing contribution to humanity.
Thank you so much for this lovely opportunity to talk about this stuff. And let's see what we have and what the future will bring us.
We'll see. Sounds good. Thanks, guys.
Cheers.
Have a good night.
Bye-bye.
See you later. Bye-bye.
Thanks for listening to the Brainstorm with Sparks and Finn. Hope you learned something new or found some food for thought. If you did, take a second to smash that like and subscribe button. Consider joining our Patreon to help Sparks and I spread the word. And then join us next time as we explore this amazing electric universe. Cheers!